Okay, so welcome to Math341 Probability. This is lecture 8. And so what we're going to be doing today is we'll talk very briefly about induction. I had asked somebody who is willing to bring a photo ID. Did somebody bring a photo ID? And you're willing to share it? Okay, excellent, thank you. Then we'll start talking about the basics of PDFs. We'll talk a little bit about random variables. And then if time permits, we'll talk about moments and expected values. And so, as always, one of the big things I want to keep emphasizing is coding. It is so easy to make mistakes. And I made a mistake in office hours this morning where I accidentally had no order in the denominator and order in the numerator. And so if you were to then write code and simulate it, you would realize you've almost surely made a mistake. It's unlikely when you do things multiple different ways that you're going to make mistakes that perfectly align and you'll get the same wrong answer. Okay, so it's really good to be able to write code and check your work, or to write code and get some data and make conjectures. This is the 21st century. It is so easy to work with data now. You can start to see patterns. Okay, so the first thing is induction. So it seems like most of you have seen induction before. This is not a proof-intensive course where I'm expecting you to be able to do proofs, but some of you will eventually take such classes. So the more proofs you see, the more that's going to help you. How many of you have either taken or are thinking of taking real analysis? Okay, so if you take a class like real analysis, you're going to start to do a lot of proofs. And so seeing proofs now is going to make things a lot easier. So the way induction works is we have some statement, P sub n, and then it works as follows. The base case is you show P0 is true. And sometimes instead of counting at 0, we might start counting at 1 or 2, whatever. You have some point where you start counting. And then you have the inductive step. Show if Pn is true, then Pn plus 1 is true. Then can conclude Pn is true for all n in 0, 1, 2, ... And the proof is basically the staircase. We know P0 is true. And we know by assumption, if Pn is true, then Pn plus 1 is true. What would be a good value of n to use? 0. So we know P0 is true. We know P0 true implies P0 plus 1 is true. So what can we deduce? So P0 is true. P0 true implies P1 is true. We can now deduce. Which is true. So what's now true? P0 is true. P0 implies P0 plus 1 is true. So what's true? Well, I'm saying we know P0 is true. We then use the inductive step that said whenever Pn is true, Pn plus 1 is true. We used it with n equals 0. So we know if P0 is true, then P0 plus 1 is true. We know P0 is true. What can we conclude?
Pn is true.
Not Pn plus 1. Which value do we now know is true? P1 is true, right? So now we know P1 is true. Now, let's go back to the statement Pn implies Pn plus 1. What should we take for n now? We take 1. And so now we know P1 is true. P1 true implies P1 plus 1 is true. What can we deduce now? P2 is true. And we just keep marching like this. So here is P0. And then here is, I'll do down here. Here's P1. Here's P2. This is the ladder that you walk up. And so there's a bunch of things you can prove by induction. let's show 1 plus 2 plus dot 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 plus n equals n plus 1 over 2. So a proof by induction. So the first thing we need is our statement Pn. And let's let be 1 plus 2 plus dot 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 plus n equals n plus 1 over 2. What's the first value of n we want to look at? 1. Or we could start looking at n equals 0. If I want to start looking at n equals 0, what should I start my sum with? I should start with 0. So I could do it either way. I could have the sum starting at 0 and do it like this, or I could have the sum starting at 1. It doesn't really matter. So then we do the basis case. So the base case. Is P0 true? So is 0 equal to 0, 0 plus 1 over 2? Yes or no? Yes. Now we do the inductive step. We have to show if Pn is true, then Pn plus 1 is true. Note when we're doing this, we're not proving that Pn is true. We're just saying if Pn is true, is Pn plus 1 true? So since Pn is true, we can assume 0 plus 1 plus dot 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 plus n equals n plus 1 over 2. What should we add to both sides? We want to show that this implies Pn plus 1 is true. What would be a good thing to add to both sides? N plus 1. So add n plus 1, and we would get 0 plus 1 plus dot 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 plus n plus 1 equals n plus 1 over 2 plus n plus 1. Well, how would we add the stuff on the right-hand side? Common fraction, right? So I multiply by 2 over 2, and this will give me n plus 1, n plus 2 over 2, which I can write as n plus 1, n plus 1 plus 1 over 2. So this shows Pn plus 1 is true. So this is one of the more straightforward proofs by induction. Any questions about how we would do this? What was the hardest part about this? Yes. So one thing is you could say, one challenge was knowing to add n plus 1. This hopefully isn't that bad because we're trying to get the statement Pn plus 1. We almost have the statement Pn plus 1 here. So it seems natural to do this. The other way you could have done this problem is you could have started off with, Pn plus 1 is 0 plus 1 plus dot 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 plus n plus 1. Does this equal n plus 1 plus 1 plus 1 over 2? And if we do it like this, we could say, oh, we recognize what this is by assumption. This is Pn. So that was one thing that was a challenge. The other thing that was a challenge was knowing what to prove. I told you it's n times n plus 1 over 2. What if I give you Pn is now 0 squared plus 1 squared plus 2 squared plus dot 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 plus n squared equals n plus 1, 2n plus 1 over 6. Do you think you could prove this by induction? So I urge you to try to prove this by induction The base case isn't that bad. After doing squares, what do you think you would try to do next? Cubes. And can you figure out what it should be? Is it always a polynomial? Notice the polynomial is a multiple of n. Well, that makes sense because if n equals 0, it should be 0. What's the leading coefficient of this? What's the leading coefficient? The leading term is 2n cubed over 6, which is n cubed over 3. On this side, we have the sum, k goes from 0 to n of k squared. How can you approximate a sum? So you should have seen this in calculus. How do you approximate a sum? You look like you want to say it. How would you approximate a sum? So this is a Riemann sum, and so you would approximate. So the Riemann sum is approximating a what? An integral, right? So this would be like integrating from 0 to n of x squared dx. What's the integral of x squared? Nope. Integral of x squared. X to the 3 over 3 at 0 and n. So that's n cubed over 3. So this is a quick test that this is at least reasonable. They're giving us the same main terms. So I strongly urge you to try to do a few problems by induction. Try to prove the sum of squares. If you want more, let me know. For a lot of them, it's pretty straightforward. You just try to find Pn lurking in Pn plus 1, and then you use the inductive assumption. If I don't tell you what the polynomial is, the problem is much harder. There is a way to do it. There is a way to figure out what those polynomials are. That's more advanced, and I'm resisting the temptation to go there. That's not the point of this class. There are ways to figure out what those polynomials are. All right. What I want to do now is prove the following theorem. Everyone in the world, and you said you have your ID on you?
I do.
May I see it?
School ID or just?
Oh, school ID is fine. Everybody's named Yanni. I don't think that's what's on my ID, but I don't want to dig out my ID right now. So rather than digging out my ID, I will just prove everybody has the same name. Is anybody suspicious? All right, I'll prove everyone has the same name. So Pn is in any group of n people, all have the same name. So let's do the base case. Is P0 true? What do you think?
P1 is true.
P1 is true. So let's do base case. P1 true? Yes. So we'll start counting at 1. If you have a group with 0 people, I could rephrase it to in any group of n people, no two people have different names. If I phrase it like that, I'd be okay. So the base case, we agree that whenever you have a group of 1 person, everybody in the group has the same name. So let's do the inductive case, the inductive step. Assume Pn is true, prove Pn plus 1 is true. So what does Pn being true mean?
These for group of people size n, all the same name.
They all have the same name. So let's consider n plus 1 people. 1, 2, 3, n minus 1, and n plus 1. Is it okay if I don't do a good job drawing the people? Okay, I have n plus 1 people. Can somebody give me a group of n people? Can somebody give me a group of, yes, Yanni.
Oh, this classroom people?
Well, no, I've got n plus 1 people. Can you give me a subset of n people from this group of n plus 1?
Oh, just 1 to n.
1 to n. Thank you, Yanni. Can someone else give me a group of n people?
1, 2, 3.
I'm sorry?
From 1 to 3.
Is that going to be n people?
Oh, n.
I need n people. So Yanni gave me 1 to n. What would you like to give me, Yanni? Thank you, Yanni. Right? So these groups are both all n people. What can you tell me about the first group of n people? Same name. What can you tell me about the group of the last n people? But look, I've got all these people in common. Everybody has the same name. Because everybody in the first group has the same name as person 2. Everybody in the last group has the same name as person 2. All same name as person 2. So all have the same name. And since we know at least one person in the world is named Yanni, we know everybody's named Yanni. What's wrong with this argument? Is there a mistake?
It assumes that n is at least 2.
Yes. So the issue, it was a bad picture. So if n equals 1, here is n equals 1, here's n plus 1, which would be 2. And now notice in this case, the groups are disjoint. So there is no common person. Note, if P2 is true, is Pn true for all n greater than or equal to 2? Yes. If you know in any group of 2 people that everybody has the same name, then in any group of no matter how many people, everybody will have the same name because you can keep splitting them off with everybody just go with person 2. So what's going on here is this is our staircase. There's a gap and we can't take that first step. There's a lot of things you can prove that are incorrect when you have this small little mistake. And if anybody's interested, email me. I'm happy to give you some other items. All right. So what I want to do now is I want to pivot to probability density, some definitions, some examples. So we say f of x is a density or a probability density function, abbreviated PDF, if f of x is non-negative and the integral from -infinity to infinity of f of x dx equals 1. So this is the continuous case. Or f of xn is greater than or equal to 0 and the sum n goes from 0 to infinity of f of xn equals 1. Now, maybe most of the xn's, the probability is 0. We're not allowing ourselves, this is the discrete case. I'm not allowing myself to sum over, say, all real numbers. This is technically summing over an at most countable set. So in the discrete case, either have a finite set or a countable set. And then it's possible to have a probability distribution that's part discrete and part continuous. We're not going to really worry about that because you can break it up into the two different cases and deal with things. So if I give you a distribution, or at least if I give you a candidate to be a probability distribution, I just have to check two things. Is it non-negative? And does it either sum to 1 or integrate to 1? This is why we care about the fundamental theorem of calculus. And this is why before class I was talking about why do we care about induction? Induction provides a way to test the claim in the fundamental theorem of calculus that the area under the curve is the antiderivative at b minus the antiderivative at a. And so if I want to use the fundamental theorem of calculus, the integral from a to b of f of x dx is big F of b minus big F of a, where big F prime is little f. Areas under curves often correspond to probabilities. If we want to check the fundamental theorem of calculus, well, what f's can we do? We could do f of x is constant. We know how to check that case. I can find the area of a rectangle. We could do f of x equals ax. This is the area of a triangle. And now more generally, if we start to do things such as, f of x is x squared, we can use induction to do the Riemann sums. And that's why I wanted to do induction today, because induction today provides a way to find the areas under these curves and give you, at least if the function is simple, a check that the fundamental theorem of calculus is reasonable, that areas under curves correspond to differences in antiderivatives. The big lie in Calc 2 is that you can integrate. You can't. Integration is hard. If I write down just a generic function, you are not going to be able to do a closed form expression for the integral. Differentiation is the opposite. Differentiation is easy. No matter how evil I am, I can't give you a differentiation problem that you won't be able to do. I can very easily give you one that you won't enjoy. I can very easily give you one that will be time consuming, but I can't give you one that you can't do. You just keep hitting it with your rules and reducing it to smaller pieces. But integration is different. Most of the time, you're not going to have a nice antiderivative. So what we need to do is we need to start finding examples. And so probably the simplest is the head-tail, right? So there's a lot of ways to do this. You could say the probability of a head equals 1/2. The probability of a tail equals 1/2. This would be the fair coin. Sometimes we do the probability of 1 equals 1/2. The probability of 0 equals 1/2. We like to do this because what's 3 plus 5? 8, okay? 17 minus 2, 15. 3 heads plus 2 tails. 3 heads and 2 tails, right? We can't really add heads and tails, but we can add zeros and ones and negative ones. Sometimes we do p of 1 equals 1/2, p of minus 1 equals 1/2. These are all basically the same distribution. We're changing it a little bit as to which is more convenient. It's nice to have a head correspond to a 1 and a tail either a 0 or minus 1. If I have it just as 1 and 0, then this is going to be very easy to keep track of the number of heads. But it's then maybe making head a little bit more special than tail. So anybody know the name of a variable like this that takes on just 2 values? So it's a binary. Other names? Bernoulli. And we often say X is Bernoulli with parameter P. And that will mean the probability big X equals 1 is P, and the probability big X equals 0 is 1 minus P. Sometimes we write the X's like this to emphasize the fact that it is a capital letter. It can be difficult to see or understand a professor's handwriting, right? And a capital X and a little x can look very similar if you're writing quickly. As an aside, this is probably one of the worst symbols in mathematics to try to understand. I'll write the tech code. So this is the complex, oh yes, the complex conjugate of the capital C divided by C. You know, it looks like a bunch of parallel lines of different sizes. You know, it can be really difficult to interpret. It is worth spending a moment or two talking about this. Whenever you are doing things, think about notation. You know, I know somebody last night, I was talking with them, they were working on one of the problems, and they were using X and Y for the variables, you know, the number of red marbles and the number of blue marbles in one of the problems. And the reason they did this is, well, we're used to looking at functions of two variables. The variables are X and Y. It's also natural to use R and B for red and blue. What's a good choice to use? And so you want things so that you can quickly look down and see what's happening, see what's going on. We typically use capital letters for the random variables, and we use lowercase letters for the values they take on. And again, the goal is to be able to just quickly look down and see what's going on. Am I talking about a random variable, or am I talking about the value the random variable takes on? A moment ago, we had a function little f, and the antiderivative was big F. That's good notation. I can just look at it and I immediately say, oh, okay, big F is related to little f in this very nice prescribed way. And I can just glance at the equations and see what's going on. So this is one of the most important random variables there is. For some things you want to do 1 and 0, for some things you want to do 1 and minus 1 as the two values. There are advantages to both. The standard one is 1 and 0. And what you can then do is you can start looking at other variables. Let's say we have n independent tosses of a coin with probability P of heads. Let capital X be the random variable of the number of heads. So what are the possible values that X could take on? We toss a coin little n times, and we count how many heads we get. 0 to n times. And it has to be an integer. So the probability X equals K is 0 if K is not in 0, 1, ... n, and it is what? So because the tosses are independent, and they're all from an identical coin, I just need to count in n tosses, what's the probability I have a string with exactly K heads? So if I give you a specific string, you know, let's say I give you H, tail, H, tail, H, tail, H. This would be probability P, 1 minus P, 1 minus P, P, 1 minus P, 1 minus P, 1 minus P, P. So the probability of a specific string is just going to be the product of those probabilities. And so the probability of this string, it would be P to the 1, 2, 3, 4, and then 1 minus P to the 5. So this would be the probability of a specific string of 4 heads in 9 tosses. But of course, there's other ways to get 4 heads in 9 tosses. How many ways are there to get 4 heads in 9 tosses? 9 choose 4. And in general, if I have n tosses and I want to have k heads, how many ways can I choose k of the n? What do you think it would be? It would just be n choose k. So it'd be n choose k, and then it would be p to the k, 1 minus p to the n minus k. So that would be the probability. Now, if the coins were not identical, imagine the first coin is always a head and the last coin is always a tail. Then all the strings wouldn't be equally likely. So this crucially uses the assumption. And so this is called a binomial random variable. How many parameters does this have? So how many things do I have to specify which binomial random variable I'm looking at?
Yeah, ask this again, sorry.
Sure. So this is a binomial random variable. What do I have to specify to tell you which binomial random variable? I have n independent tosses of a coin with probability p of heads. X is the random variable that counts the number of heads. What are the inputs I need to give you? N and p. And so I think you write n first and then p second. You can do it either way. So this is a binomial random variable. Now what's interesting is let x k be Bernoulli p is the random variable of a head on toss k. Then our random variable x is just x1 plus xn. We're going to do a lot more with this. One way to view this Bernoulli random variable is it's a sum, the binomial random variable x is it's a sum of Bernoulli random variables. I could flip all n coins at once, have them come down and look at what happens, or I could flip them one at a time. It doesn't matter. And so these two are the same. And one of the big things we're going to see is that we can deal with sums somewhat. Okay. So there's a lot of different random variables we can do. Who here has taken a stats course before? Okay, good. So the next one you should have seen, and there are 2 different ways of doing it. Now there's the way I like and there's the way I don't like. The exponential random variable with parameter. Do you normally use lambda, theta, lambda? So how would you do your exponential random variable with parameter lambda? What's your density? Does anybody remember the exponential random variable from stats? So one way is e to the negative x over lambda, and then a 1 over lambda so that it integrates to 1. Or lambda e to the negative lambda x. So sometimes in order to maybe avoid confusion, sometimes people might use a different letter if we're doing it this way, or omega. What's the relationship between lambda and omega? Yeah, they're inverses. Which way is better? I'm not saying which, did I say which way I like? Good. Which way do you think I like? The first or the second? The second. Why the second?
Simpler.
There's no division. right? Doesn't the second one seem better? But why am I writing it second if it's the better one? So later on, we haven't done expected values yet, we haven't done means yet, but anybody who's at a school like Williams has almost surely been in a competitive environment at some point in your life. You may not have cared, but there will be people around you who have cared. I remember when I was a sophomore at Yale, I was visiting a friend of mine who was a freshman at Harvard. We'd gone to high school together. And outside their math or their physics class, the professor had the student IDs and they had the grades on the exam that they just got back. And the professor listed the mean, the standard deviation, as well as the next two moments, the skewness and the kurtosis, so that the really grade conscious Harvard students could see how they're doing relative to their classmates. They gave the first 4 moments of the distribution. The standard deviation was not enough. They needed to know how skewed was the distribution. And we'll talk later in the semester about what all that is. For the most part, most humans just look at the mean and the variance, or the mean and the standard deviation. What's the average value and how spread out is it? So everybody should be aware of what is the average value of a distribution. So the average value, expected value, the mean is the following. I write it as, fancy E for the expected value, and then the colon equals means this is a definition. And I'm just going to integrate from minus infinity to infinity of x, f of x dx, or if it's discrete, I'll just do xn, f of xn. So this is just calculating the average value. And what we're basically doing is saying, take every value that the random variable attains and weigh it by the probability you took on that value. You've all done calculations like this if you're trying to estimate your grade in a class. The final is 40%, so I take my final grade and I multiply by 0.4. The midterm is 30%, so I multiply that grade by 0.3, and so on and so on and so on. So let's calculate the expected value for the 2 different exponentials. So the expected value for the first exponential would be the integral from 0 to infinity, and here this is for x greater than or equal to 0, of x times 1 over lambda e to the negative x over lambda dx. So anybody remember how to do that integration? So step 1 is, I'll do some nice transformation. I'll let u equal x over lambda. So du is 1 over lambda. So this is the same, and then x going from 0 to infinity is the same as u goes from 0 to infinity. So this is the same as the integral from 0 to infinity. X over lambda is just u, e to the minus u, and then dx is, du should be dx over d lambda. So du, so dx is lambda du. So I have to integrate u e to the minus u. How do we integrate u e to the minus u? I'm sorry? Yeah, and so if we're going to do integration by parts, I probably don't want to use u as my variable here, because I like to use u and dv. So we'll just change things. This is the nice thing about doing it like this. Instead of using the letter u, let's use the letter t. So t is x over lambda, dt is x over lambda. So we now get, t e to the negative t lambda dt. So we'll let u equal t, dv equals minus e to the minus t dt. Du is going to be dt, and then v is negative e to the minus t. So when we integrate, we get uv, so we'll get minus t e to the minus t at 0 and infinity, minus v du, well, the minus sign is reinforced, and we'll have the integral from 0 to infinity of just e to the minus t dt. What is negative t e to the minus t at 0 and infinity? At 0, it's just 0. And at infinity, I've got a e to the minus infinity, which is decaying much faster than t is growing. So does everyone agree that the boundary term is just 0? And now I'm just integrating e to the minus t from 0 to infinity, that you can just do, and you can see that that equals 1. So this equals 1. And so since I have this extra lambda over here, I see that this integral is just equal to lambda. If I were to do the other way, if I were to do the expected value of the other one, I would be integrating from 0 to infinity of x w, or omega e to the minus omega x dx. What do you think that integral would be when the dust settles? Can anybody do that integral quickly in their head? Does everybody agree that the first integral is lambda? Yes. Good observation, Yanni. Of course, I could have said that to anybody. Oh no, wait, we proved I couldn't. It's 1 over omega. Why? Because w or omega looks like 1 over lambda. So if I just replace omega or w with 1 over lambda, it's the same as the integral I just did. So I get that the value is lambda, but lambda is 1 over w. I don't have to do the algebra. So if I have an exponential random variable with parameter lambda, then its expected value is lambda. If I do it the other way, its expected value is 1 over omega. I'd like the parameter to be the mean, right? That's why I prefer the first one, because in the first one, I'm looking at x over lambda. Lambda is the mean. In the other one, yes, there's no division. I get w times x, but now w is actually the 1 over mean parameter. And so this is why I actually prefer the first. Okay. So there's a lot of different probability distributions we can look at. I didn't write down the uniform random variable. If I give you a uniform random variable, so x is uniform on AB, means p of x equals 1 over b minus a if a less than equal to x less than equal to b and 0 otherwise. So this would be a uniform random variable on the interval AB. I need the area under the curve to be 1. I'm going from A to B. If it's uniform, I want my density to be constant. So what height do I need so that the area is going to be 1? It's going to be 1 over b minus a, so that when I multiply by the length b minus a, I get 1. So the most common uniform random variable is the one from 0 to 1. And so let's say x is a uniform random variable on 0 to 1. One of the most important questions in mathematics is, if I have a known random variable and I do a transformation to it, what can I say about the new random variable? Does it make sense if I know the distribution of x, I should know the distribution of x squared, or x cubed, or exponential of x? Whether or not it's still nice and I can extract it, it's much harder. What if I want the distribution of, say, x squared minus x over x plus 5 cosine x? Right? But if I know what the distribution of x is, I should be able to figure that out. So what I want to do now is I want to take a uniform random variable on 0, 1, and I want to square it. And I want to know, can I calculate what is the distribution of y equals x squared? What is its probability density? And I'm going to show you an extremely powerful method that at first place, it should seem like there's no way this could work, because I'm going to ask you to do something I just told you earlier in class you can't do. I'm going to ask you to integrate in closed form. Can you integrate in closed form? No. So you're out of luck, except for the fact that I happen to be in a compassionate mood today. And as soon as you integrate, I'm going to immediately ask you to differentiate what you got. Can you do that? Yes? If I ask you to integrate and then differentiate, that's not so bad. All right? So what we're going to do is we're going to introduce something called the CDF. The cumulative distribution function, called the CDF, is the probability that x is at most little x. And so if little f is the density, big F is the CDF. We often do something like this. I often put subscripts on my densities. Why might I put a subscript? Why not just use F and capital F? So you should always do things for a reason. You really want to think about notation. Why is this worth doing? Well, F is the density of my random variable. Which random variable? What if you have more than one random variable that you're discussing? Such as, oh, I don't know, x and x squared, right? I want to be able to quickly look down and see what does it go. I could use little f for x, and I could use maybe g for x squared. Or a good general notation is put as a subscript what the variable is. So I could do maybe f sub x and f sub y. Or I could do maybe f sub x and f sub x squared. By doing this as my notation, I can quickly see what's going on. So what we have is big F of x of little x is the probability big X is less than or equal to little x is the integral from minus infinity to little x of the density. So I'm just finding the area. So, if you look at what's going on, here is t. Here's my function, and I'm just finding the area under the curve up to t. And that's the cumulative distribution function. Now, what do you think the cumulative distribution function at negative infinity should be? What's the probability you take on a value of at most negative infinity? It's just zero, right? The probability that you're at most negative infinity is zero, right? So this is why I'm not writing this as big F of x at little x minus big F of f at negative infinity, because this is zero. So we don't write. Right? No matter what random variable I give you, it's not going to have a value of minus infinity or smaller. So now, what happens if we take derivatives? So take derivatives. So big F prime of x at little x, that's the derivative of the integral. So that's the derivative of big F of x at x minus big F of x at negative infinity, but the negative infinity is zero. So this is just, oops, sorry, this is an x, not a t. So this is just the derivative of the antiderivative. What's the derivative of the antiderivative? It's just our original density. So another way of thinking about this, if this is t, if I go to t plus h, and I look to see what's the amount of area over here, this would be big Fx of t plus h minus big Fx Didn't leave enough space. Minus big F of x of t over h. And that's going to basically become the integral from t to t plus h of the density. Oh, I'm sorry, these should be x's. X plus h. So I'm integrating from x to x plus h of f of t dt. Well, if h is really small, and I divide by h, if h is really small, does the function change that much over an interval of size h? No. So this is going to be approximately 1 over h times the value of the function at the left endpoint times the length of the interval, and you see the h's cancel. So this is another way to see why the derivative of the cumulative distribution function is the probability density. If I just look at increasing by just a little bit, subtracting and dividing by h, that's how I take the derivative. That's giving me the probability of a small region divided by the length of the region. That's going to go to the density. So for any nice continuous distribution, this is what's going to happen. What's wonderful about this is I don't need to know what big F is for a lot of these calculations. There's some big F, and I can work with it. This is similar to in the proof of the fundamental theorem of calculus, you might have seen the mean value theorem used, which says there is a point with these wonderful properties. I can't tell you where it is, but there is such a point. There is a function big F. I don't know what it is explicitly, but there is such a function. How can I use this? So now, let's continue. And so we have x is uniform on 0, 1. So the density of x is 1 if x is between 0 and 1 and 0 otherwise. And we want y to be x squared. And we want to find out what is the density of y. Well, let's calculate the cumulative distribution function of y. So this is the probability that y takes on a value at most little y. And then if we can figure that out, if we then can differentiate, then we would get the density of y. So this is going to be the same as the probability that x squared is less than or equal to y. So what does it mean for x squared to be less than or equal to y? So what does it mean for x squared to be less than or equal to y? So I know how to calculate the probability of x. I want to get a probability of x. I have a probability of x squared. I want to pass to the probability of x. So if x squared is less than y, it's the same as what? What must be true about x if x squared is at most y? Almost. So x is less than or equal to the square root of y. What else could be true? Negative, right. So we know x lives between minus root y and root y. So this is the same as the probability minus root y less than or equal to x less than or equal to square root of y. So to calculate the probability that big Y is at most little y, it's the same as calculating the probability that big X is between minus root y and y. But what do we know about x? X is a uniform random variable. So what's the probability that x is less than 0? 0. So this is the same as what probability? It's just x less than or equal to the square root of y. And so to do that, we now just need to integrate from 0 to the square root of y, the density function. Well, this is nice because we have a uniform random variable, right? So the density function is just 1. And this is one of the nicest integrals I can give you. What's the integral of 1 from 0 to root y? It's just root y. Yes? Because the function is constant and I just multiply by the length. So we've just shown that the cumulative distribution function of y is equal to square root of y. So the density is going to be 1/2 y to the minus 1/2 for 0 less than or equal to y less than or equal to 1. Do you think that this is reasonable? Is there anything you can do to check? What can we do to check? So we're claiming that this is the density function for capital Y. How can we check and see if this is a density function? What must the density function satisfy?
We integrated.
Good. So if we integrate from 0 to 1 of 1/2 y to the minus 1/2 dy, that's going to be 1/2 y to the minus 1/2 becomes y to the 3/2 divided by 3/2, evaluated at 0 and 1. If I made a mistake. Oh, no, sorry, no, so not 3/2, 1/2. And so we get 1/2, and then we get 1 over 1/2 minus 0 over 1/2, which is 1. So it does integrate to 1. What else do we need to know for probability density function? It integrates to 1. Good. What else? What's the second condition? Always positive. And 1/2 y to the minus 1/2 is always greater than or equal to 0. Now, when y equals 0, it actually explodes and it's plus infinity, but it does integrate to 1. So this seems reasonable. So this is called the CDF method. So this is one of the most important problems or theorems we can do in the course, because it tells you if I know the distribution of one random variable, I can often figure out the distribution of another. And frequently, we first have to integrate and then immediately differentiate, so we'll be okay. So there's a lot of more interesting problems that you can do along these lines. This time I might come back and do some more of them. Let's just jump a little bit ahead. Let's take as a density 2 plus 3x minus 5x squared for x in 0, 1. So the first question is this a density function? Well, if we plot it, it is non-negative. And I just put a little bit of notes just because it's probably been a while since any of you have had to plot things by hand. The first derivative indicates whether or not the function is increasing or decreasing. So if I calculate f prime of x is 3 minus 10x. So when x equals 3/10 or 0.3, the first derivative is 0. If x is greater than 0.3, the first derivative is negative. If x is less than 0.3, the first derivative is positive. So my function is increasing up to 0.3 and then decreasing afterwards. So this gives me a little bit of a sense of what's going on. We then plot what's going on at 0 and 1, the endpoints, to just get the values. And this gives me a quick sketch. If I now do the integration, and I didn't want to risk doing this live, and find the area under the curve, we get 11/6. So could this be a density? No. What should the integral equal if it's supposed to be a density? It's supposed to be 1. We got 11/6. But we can make it a density by just multiplying by 6/11. And now if we multiply by 6/11, since the integral of f was 11/6, the integral of 6/11 times f will just be 1. So frequently, if you have something that's non-negative and integrates to a finite non-zero number, you can correct it. You can rescale it. And so, the more general thing is just, if you have f of x is non-negative and it integrates to something that's finite, then just divide by the integral. Is there anything we need to know about that finite number? So this is a co-listed class, but it's partly a math class. So when you look at this expression, this should always be a danger sign. What are you afraid of? Division by 0. So what do we want to assume about this finite number? Not 0. That's a really mild condition to put in. All right. The only way it's going to be 0 is essentially if the function is identically 0. And I shouldn't be considering that as a probability. So this is allowing me to renormalize. Okay. So I want to spend the last few minutes and motivate a little bit of the big theorem for the end of the class. Not today, but the semester. So we talked about a uniform random variable. There's also discrete uniform random variables. And one of the most famous examples is a die. So I will use the Rubik's Cube today as a die. It has 6 sides. Each side has a color. We can pretend the colors are the numbers 1 through 6. And if I roll it, whatever color comes up top or whatever number comes up top, that's my outcome. And so unlike a coin that only has 2 possibilities, the die has 6. And if it's a fair die, each one happens what percent of the time? 1/6. And so that would be a discrete random variable with each thing happening 1/6 of the time. What this tells us is you can review the Bernoulli random variable, where p is a half, as a uniform random variable. What if we roll 2 die and we look at the sum of the roll? So how many possibilities are there if we roll 2 die? How many pairs could we get? 36. And so to save time, I wrote down some of them. There's one pair that has a sum of 1. I'm sorry, that has a sum of 2. 1 and 1. There's one pair that has a sum of 12, 6 and 6. There's 2 pairs that have a sum of 3, 1 and 2 and 2 and 1. There are 2 pairs that have a sum of 11, 5, 6 and 6/5. And what you can see is every time I increase my number by 1, coming down from the top or up from the bottom, the number of pairs increases by 1. Until when we get to 7, there's going to be 6 ways to get a 7. 1 and a 6, 2 and a 5, all the way down to 6 and a 1. And so you can ask, what's the probability of the sum of 2 die? And so what's the probability that we get a 2 for the sum? 1/36. What's the probability we get a 7? 1/6. So what we see is uniform plus uniform is not uniform. Uniform plus uniform is actually a triangle. So the sum of 2 discrete uniform random variables is giving us a triangle. All right. So for so many things in life, it comes down to, can you look at things the right way? So I've put the picture here. How many of you have never seen a Rubik's Cube? Everybody at least has seen a Rubik's Cube. This Rubik's Cube is a little strange. Its sides are 2 by 3, not 3 by 3. And the top, it does have 9 things, but they're kind of strange. When you try to turn the red side, it doesn't seem to turn. You have to hold it at a 60-degree or 30-degree angle, and now you can see that it's 3 by 3. The whole point of this was to get you to look at things the wrong way. Once you realize that if you look at it like this, it's the same as a standard Rubik's Cube with pictures on it. You have to be a little bit careful. If you have a normal Rubik's Cube that's mono, that's just straight solid colors on each side, you can't tell if the center square is rotated. So this cube is like a regular Rubik's Cube with pictures on it. It's solved the same way, but you have to know to hold it at a 30-degree angle. If you don't see that, you go crazy. You can have it look very strange. I once had some fun with the airlines, and converting this into a nunchuk. And so a lot of math is about trying to find the right way to look at things. So here is a uniform random variable from -1/2 to 1/2. And then I'm looking at a rescaled random variable. Is there anybody here who has not seen the concept of the standard deviation? Okay, we haven't officially covered it in this class, but I'm assuming by now everybody has seen standard deviation. We will cover it formally. I'm dividing my random variable by its standard deviation. What is the standard deviation of y at this point? If I take x and divide x by its standard deviation, what's the standard deviation of y? 1. So I've just rescaled. I want to compare apples and apples. So I've rescaled x to have standard deviation 1. N0, 1 means a normal distribution with mean 0 and standard deviation 1. And so that is the gold curve. And the blue curve is the uniform rescaled to have standard deviation 1. Does the uniform look like the Gaussian? What do you think? Do people agree that there's a difference in shape? All right, let's look at the sum of two uniforms versus a Gaussian. What do you think? It's not bad. Amazing how quick the sum of two uniforms is to a Gaussian. Building on the sum of two uniforms, what should I do next? I'm sorry? 3. No. Not 3. What should I do? 4. Because I know what the sum of two uniforms is. And so now I can do that sum with itself. And it's technically easier to do things like that. Here is the sum of 4 uniform random variables rescaled to have standard deviation 1 versus a Gaussian. Good fit, bad fit?
Good fit.
I'd say good fit. What should we do next? 8. Let's do 8. And by us, I mean mathematical. Here is the sum of 8. That's a pretty good fit. Now, remember earlier how we calculated using the CDF method the formula for the density for x squared given x? It turns out you can calculate formulas for sums if you know the formulas for the individual densities and they're independent. We saw a special case of that earlier today. What did we see earlier today where that was true? Where did we see sums of random variables that we knew was another random variable that we knew? We saw that in heads and tails. If I flip n coins, that's the sum of n independent Bernoulli random variables. That was the same as a binomial random variable. This is looking like a sum of uniform random variables is normal. Not only is that true, but they don't have to be uniform. Basically, the sum of anything nice converges to uniform, converges to Gaussian, converges to normal. Now, we have an explicit formula for the binomial random variable, which was the sum of Bernoulli's. As a painful homework problem, I could ask you to write down what is the formula for the sum of some number of uniforms. And we haven't quite done the techniques, but there's a chance you could figure it out. Or I could just show you the slide. Any preference? Somebody better speak or slide. Okay, slide wins. So here is the density for the sum of 4 uniform random variables rescaled to have standard deviation 1. Lovely numbers, huh? I hope nobody thinks I did this by myself. Right? You feed this into Mathematica. Could I have Mathematica do 8? Probably. 16? Probably. Would you like to work with this? So this is early in the semester. You should always be able to answer the following question about a class. Who gives a shit? Why am I learning this material? What can I use it for? You do not want to do this. You do not want to be working with things that have horrible split definitions like this with all this stuff. What if instead of working with that, you could say, hey, it's almost a Gaussian. And we have nice formulas for Gaussian. Why don't we just replace it with a Gaussian? That's the big point of the central limit theorem, is that rather than trying to write things down explicitly, we don't have to deal with that. Okay, so we've got a few minutes left. So we've already talked a little bit about moments and expected values. More generally, the kth moment of x with density f sub x is the expected value of x to the k, and we'll define that as the integral from minus infinity to infinity of x to the k times the density at x dx. And certain values have names. So the mean, which we denote by mu, is the expected value of x, which is just the integral from minus infinity to infinity of x, fx of x dx. The variance of x, denoted sigma squared, is sigma squared is the integral from minus infinity to infinity of x minus mu times the density dx. So this is measuring how spread out things are. Now, I was talking about the kth moment, but here I'm not looking at x squared. Sorry, I'm not looking at x squared. I'm looking at x minus the mean squared. I'm measuring how far away am I from the mean, and I'm weighting it by the probability I take on that value. So the smaller the variance, the more tightly compressed things are. It turns out if you do some algebra, you can show that sigma squared is the expected value of x minus mu squared is the same as the expected value of x squared minus the square of the expected value of x, where the expected value of g of x is defined to just be the integral from minus infinity to infinity of g of x small x times the density dx. So the moments is just very nice. It's taking g of x to be x squared, x cubed, x to the fourth. And the hope is that if I can understand the moments, those are really simple choices of g. The goal is if you understand the moments, maybe you can then understand the distribution. And so one way to calculate the variance is to look at the integral of x minus mu squared. And that's basically just the expected value of x minus mu squared. Another way is to look at the second moment, the expected value of x squared, and subtract off the square of the first moment. Now, I have been harping all day about the value of notation. When you see something defined by sigma squared, what should your thought be? If I'm defining the variance as sigma squared, what do you think is the right thing to look at? Not sigma squared, but what? Sigma. So the standard deviation is sigma is the square root of sigma squared. And that has the same units as the mean. And that's one of the reasons why the standard deviation is so nice. It's on the same units. If I ask you, how tall are you? Maybe on average, you're around 5'7", if you look at college students. What's the fluctuations about 5'7"? You shouldn't be giving me fluctuations in something like feet squared as units. That's an area. I want something linear. And that's why the variance is not a great unit. It's the standard deviation, it's the square root, that's the more natural one. All right, so this is a good place to stop. Have a good rest of the day, and I will see you on Thursday.